This is a screencast on the difference between continuity and uniform continuity. Now I'm going to examine two functions on the same open interval, 0, 1. 1 over x, which looks very approximately like that, and x squared, which looks very approximately like that. And I'm going to test the continuity at some nice points. 1 over 2, 1 over 3, 1 over 4, 1 over 100, and 1 over n. So basically anything that looks like that. And I'll test the continuity on both of them. And I'm going to fix epsilon bigger than 0, and I'm going to see what the delta has to be. So for each of these 1 over n's, I'm going to figure out what the delta is. And to look at this function, what I need is, given an x, 1 over x minus 1 over, well, my y value here is, say, 1 over n. So it's 1 over n has to be less than epsilon, which is the same thing as saying 1 over x minus n is less than epsilon. And this is whenever x minus 1 over n is less than delta. So I have two inputs along the x-axis. I have an x and I have 1 over n. And when I plug them in the function, I get 1 over x and 1 over n. And I need 1 over x minus n has to be less than epsilon. Great. Let's do some algebra. And if I combine these by doing denominators and all that, I get nx minus 1 over nx. This thing is equal to that, which is, I could factor on n on the top, which is positive, so I don't need to worry about that, over nx like that. The n's cancel. And I'm left with x minus 1 over n, which is good because I can make that less than delta, all over x. And I want this to be less than epsilon. Well, this is a little bit of a problem because I don't know what x is, right? If x is super small, this thing's getting really big. So let me put a bound on it. So for 1 over n, I'm always just going to cap it. Maybe I'll draw it up here. For 1 over n, I'm going to restrict delta so that I can only look between 1 over 2n and 1 over 3 to n, which means that my deltas for all these now become mins. I have to look at the minimum, the minimum, and the min is, the minimum is 1 over 2n, and something else. Well, here n is equal to 2, so I get 1/4, a minimum of 1/4 and something else to be determined, 1/6, 1/8, and 1 over 200. And notice, in particular, as I get closer to 0, as I move to left, these numbers are getting smaller. Certainly, 1/4 is bigger than 1 over 200. So what I can do is I can bound this by x minus 1 over n over 1 over 2 to the n. Okay, I made a quick algebra mistake, so I'm just going to fix this because I don't want to have to redo the whole screencast. Right? When I combine these fractions, I don't actually get an n into the denominator here. So that n should be there. That n should not cancel, so I'm just going to replace that. I just made a stupid algebra mistake, like so. So n over 1 over 2n, so this means that I need 2n squared, x minus 1n, is less than epsilon, which is the same thing as saying x minus 1 over n has to be less than epsilon over 2n squared. So my generic term here is that to test for continuity at 1 over n, I need the minimum of 1 over 2n and epsilon over 2n squared. So plugging 2 into this formula, I get epsilon over 8 here. I get epsilon over 3 squared, 18. And I get epsilon over 32. And when I get 100, I get epsilon over 20,000. I'm going to stop here, and I'm going to do the next example in the next screencast.